we're going to look at two types of full wave rectifiers. The first is something called a center tapped transformer. And so with our center tapped transformer full wave rectifier, as advertised, of course, we have a transformer where on the secondary side, we have tapped the coil at the very center, and we're going to connect that to ground. So we have this transformer, our primary side over here, our secondary side over here, which is essentially divided into two. And of course, keep in mind that our secondary voltages Vs are directly proportional to our input voltage. And in this case, they're going to have the same polarity because of the dot convention. So we've got positive here, here, and here. So our Vs are proportional to that V input. And so now that basically reduces our problem to looking at how do these diodes D1 and D2 behave as that voltage varies, because of course this is an AC voltage VI, which means that these are AC voltages Vs. So they're going to be positive sometime and negative other times. So one thing to note before we get too far into this analysis is that, of course, compared to our half-wave bridge rectifier, we've added one additional diode. So just like we talked about in our introductory video, as we're going to see, we're going to have more efficiency, but our circuit is becoming more complex. Okay, so let's kind of think about it in terms of we have some voltage Vs, which is being applied to this point here. So at this point for D1, we're basically applying a voltage Vs directly to the P side, because remember, we can always sort of go back and think of this as a P-in junction. Whereas down here on D2, to sort of make things a little easier, we can think about this as negative Vs, just because it's the negative polarity that's attached to this. So I think that's going to make it a little bit easier to sort of visualize what's going on. So again, this Vs, in order to turn on our diode D1, let's look at that top half first, is going to need to overcome our built-in voltage V gamma, or our cut-in voltage V gamma. So let's say for Vs greater than our V gamma, what's going to happen is our diode D1 is going to become forward biased. Okay, and so let's do this in, let's say, orange. So for our Vs greater than V gamma, we're going to have some current that's flowing in this direction through our diode and comes down through our resistor, giving us some usable output voltage. However, at that same time, if our Vs is greater than V gamma, that means that this is going to be a negative voltage being applied here, and if our P side is more negative than our N side, our diode is going to be turned off. So we can come down here and say that for this case of Vs greater than V gamma, our D2 is going to be reverse biased. So we're not going to have any current flowing through our D2. Okay, so now, as you might have guessed, we can kind of flip that around. Let's now say that this negative Vs, so negative Vs, becomes greater than V gamma. And so, of course, in this case, our D2 is going to become forward biased. And let me separate these a little bit so it's easier to sort of keep straight. We don't want to get our two cases mixed up there. Okay, so in this case, let's do this one in brown. Well, let's do something a little different than green. Let's do pink. Okay, so for the case of negative Vs greater than V gamma, our D2 is now conducting, so we're going to have something that looks like this. We're going to have current going this way and through our resistor. So again, we have some usable voltage V out that's going through our resistor R. However, now because our Vs is negative, because remember our V gamma typical values of this V gamma are on the order of 0.6, 0.7, so that means our Vs is lower than negative 0.7. So if we have a negative Vs, now we have a negative voltage. We have a negative voltage here relative to this side, which is of course going to make that D1 diode reverse biased. And so what we're seeing is basically for half of the cycles our D1 is conducting and half of the cycles our D2 is conducting. So we can sort of put this all together graphically. and have a look at our output voltage that way. Okay, so I've sort of, again, already got a plot started for us here. We see that we have our, so let me go ahead and label a couple things here. We have our Vs max right here, and this would be our Vs min. And then we also have our V gamma and our negative V gamma. And so the curve I already have plotted here is our Vs. So note, Vs is applied in two places. We have sort of the top half and the bottom half here. Okay, so for that Vs greater than V gamma, for this first case, we said that our D1 is forward bias. So Vs greater than V gamma, so that occurs, again, we can kind of zoom in. We can see that that occurs for this point here. So from that point onward, our diode D1 is turning on. So we get something that looks like this. So it's off until we reach that point, and then our diode D1 turns on, and we get something that looks like this. And that's going to stay on until we reach, until our Vs goes below V gamma. So let me switch here. So until our Vs drops below V gamma, that's where that's going to cut off again. Okay, so this, again, we're going to have a difference of V gamma. So this difference right here is a difference of V gamma, the cut-in voltage. And during this time, we have our diode D1, which is on or conducting. So now that's our first case. Remember, our D2 is off during that time. However, as our Vs continues to decrease, at some point our D2 is going to turn on. So if we sort of rearrange this a little bit, we can of course move this over to the other side. We have to switch our inequality. So we can say when our Vs is less than negative V gamma, that's when our D2 becomes forward biased and our D1 reverse biased. So of course we can see that's the case for this right here. And here's where it sort of changes again. And so between these 2 points, neither diode is conducting, so we have zero output voltage. And so let me go ahead and write this green curve as our output voltage. Once our D2 begins conducting, though, we have the same amount of current across R that we did before, and note that it's in the same direction. So both of these currents are in the same direction through our resistor. So what that means is that we're going to have our curve for when our D2 is on is going to be the same shape and height as for our D1. And we get something that looks like this. And so this is for our D2 on. And so of course we just keep repeating that between sort of these 2 points here. Both diodes are off, not conducting, and then we have our D1 turn on. And then they're both off for a little while, and then our D2 turns on. And again, that's going to be V gamma below, and then our drew that a little far, then we get something like that, and so on and so forth. And so again, just to label explicitly, we would have our D1 conducting for this half cycle, our D2 conducting for this half cycle. And so of course we can see this is going to be much greater than the roughly 33% that we saw in the previous example for a half-wave rectifier, because the only times that we're not conducting are between sort of these times when our magnitude of Vs is less than V gamma. So that is our center tap transformer full wave rectifier, and we're going to look at another type in our next video.